school-wise. So, what we're going to do today is a shorter lecture, and because I had a meeting this morning that I couldn't miss for office hours, what we're going to do is I'm just going to finish out this chapter, and then I will be here for any questions that you guys have. So kind of make up the office hours time. I don't know if anyone went to my door this morning. The morning office hours on campus don't seem to be too popular, but anyways, I did get one person one morning. Yeah, so that's all we're going to do today. Also, I noticed that a few of you subscribe to the YouTube channel, which is good because it's taking forever to upload the videos. And then sometimes I just plug in my phone and I'll just leave it there uploading, and I'll go to bed, and then I'll come back and I'll notice that like 3 of you watched the video at like 2 a.m. And I'm like, what? But anyways, so yeah, they're usually there. I just haven't linked you on Canvas yet. So just so you know, yeah, I try, and then sometimes it's like 17 hours later, it's like, you still have 19 minutes. I'm like, gosh. Yeah, it just kind of depends. Some days it's like, boom, in 45 minutes and it's uploaded, and then sometimes like, yeah, 48 hours later, it's still like 19 minutes and counting. All right. Okay, so last time we talked about Fischer projections. So I'm just going to kind of review this a little bit because I know at the end of lectures we're starting to get a little bit filled up with information. And it just kind of helps when we hit it again and you guys can see it again. So Fischer projections, this is just another way of drawing molecules. So a lot of stuff that we do in here, I show you something, I'm like, this is what it means, and then I show you another thing, and I'm like, this is another version of that. And then here's the third and fourth and fifth version of that. And you guys kind of have to recognize that these things are telling you the same thing. Well, here's another one, the Fischer projection. And we took a look at this little molecule here that had these cool little springy things on them. And we said that if we put the blue ball forward and the green ball back, so again, the wedge means it's coming out at you, and the dash means it's going back into the board. And then we have the red one over here, and just pretend this one is black. And then we squish it. What it's going to look like is this, which is right here. And then we drew all of the atoms except for the carbon in the middle, because we said with the Fischer projection, when you have the cross, that means that it's what kind of carbon? It's a chiral carbon. So it's bonded to 4 different groups there. It is asymmetric. So asymmetric carbon, chiral carbon, chirality center, stereo center, blah, 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 blah. All the different names for that kind of carbon there. So are we all right with that, friends? And then we said if we have a big old molecule and it's drawn in a Fischer projection, you can tell right away how many chiral carbons there are. You don't have to go through the process like we have this week in lab of trying to figure out what's chiral or not and putting a little asterisk by it, okay? So it just tells you how many chiral carbons you have. And then we took a look at this right here, and we had argilglyceraldehyde, the Fischer projection for that, and alanine right here. And what this one is saying is when you have, let me see if I can line these guys up. Okay, so we've got our blue and our hydrogen, and then, okay, so I hate these ones. Oh. So our red is back, and our green is down, just so I can get the colors coordinated for you guys. Okay, so what we did is we said, okay, here's some other ones and blah, blah, blah. I'm talking about this, and you guys are probably tuning me out about this time because it was the end of lecture, right? And now here we are again. So yay, we're all refreshed. So what the Fischer Projection projection does is not only tells you where there's a chiral carbon, but it also says anything that's horizontal is pointing out at you, and anything that is vertical is going back into the board. So if we wanted to draw that with dashes and wedges, it would look like, see up there, how you have the two wedges coming out at you and you have the dashes going back? Does that make sense, friends? Kind of, sort of, maybe? And then this over here is telling you that if you hold the, let me switch here. Ooh, okay, so if we just turn it around so that the green is down and the yellow is up. It's the same molecule because I didn't break any bonds. I didn't make any new bonds. Does that make sense, friends? I just turned it. Okay. So I went from this to this. Okay. What this is showing you is that with a Fischer projection, if you hold one of your atoms, you can switch the other three all you want around, like this or the other way. You have free rotation there. And then this is the other way that we could draw it, like this. Putting the hydrogen up, and there we go, nitrogen's that way, the green one's down that way, and the red one's this way. Okay, so there's a bunch of different ways that you could draw it. It's gonna represent exactly the same thing. Okie dokie smokies? So are we kind of okay with the Fischer projection? So the point of this is showing you that this is the same as this, is the same as this, is the same as this. Kind of, sort of, maybe, friends? Okay, questions for me on this? Yes, no, maybe so? Okay, silence, all right. And then we looked at a more complex one. And the Fischer projections are going to become important when we do sugar chemistry. So we have a whole chapter on carbohydrates. Everybody's favorite kind of molecule, right? Potatoes, sugar. Okay. And we said if you have something that's big like this, with a Fischer projection, boom, you can tell how many chiral carbons you have. How many chiral carbons here, friends? There are 4 because you have 1, 2, 3, 4, the ones that are drawn at the cross points, right? Yes, no, maybe so? Okay. Now, weird. There's some carbons that are drawn in and some carbons are not drawn in. Well, in the Fischer projections, you don't draw the chiral carbons in. They come at the cross point like that. And the carbons that are not chiral, that are achiral, they're often the ones that are drawn in. And we can check that out. You see down here we have CH2. So this carbon is bonded to 2 of the same thing. So is that carbon right there chiral? No, because it's bonded to 2 of the same thing. What about this one up here? Well, it's drawn in as a C, and I just said the ones that are drawn in are not chiral, right? But you're probably like, what is CHO? I don't know what that is, lady, right? That is just shorthand for this. I'll show you guys. So that means this. C double bond O, and then you have a hydrogen right there, and you can draw in the lone pairs on oxygen if you need to. And then the rest of the molecule, all of this is down here. So that's just shorthand for this. And we know that if you have a carbon that's double bonded to something, is it chiral? No, because the way we think about this is like it's single bonded twice to the same thing. So we say that one is not chiral. Is this jogging our memories? Kind of, sort of, maybe? Okay. So this one up here, friends, how many chiral carbons there? One on the top. 2, you can see that right away. You don't have to figure it out like we did in lab, right? The Fischer projection just tells you. And then down here at the bottom, chiral or not? Not. Achiral, it's bonded to 2 of the same thing, the H2 there, okay? And then at the top, this is a different way of writing this same thing. And it kind of tricks you, makes you think it's a carbon bonded to a hydrogen, and the hydrogen is doubly bonded to an oxygen, but no! Because hydrogens only ever do a single bond. How do we know? Well, we just learned that. Sorry. Okay. All right. And then we said, well, what does this actually look like? Because you don't have a bunch of flat little molecules dancing around in your beaker. And we talked about how it was like this crazy thing like this. Do you guys remember that? How I went through each and every carbon and how these ones were pointing out at you and then those ones were pointing back. Do we kind of sort of remember that? Do you guys need me to do it again? No. No, please don't do that. Okay, well, if there's anyone out there that would like me to do it again, that's what you pay me for. Okay, and then what we said is if you interchange any two of your groups on an asymmetric carbon or a chiral carbon, that you're going to get the other enantiomer. So if we have this right here, and it's R, and we pluck two of these off, and we interchange them, and we leave the other two as is, okay? Doesn't matter which two you pick as long as you leave the other two. So you break those bonds and you make new ones, you switch them, you're gonna end up with the other enantiomer. So if you take an S and you pull these two off and you switch them, you would end up with which enantiomer? The other one. The R. That's exactly what the slide says. If you have an R and you pluck two of the groups off and switch them, then you'll end up with the S enantiomer. If you have an S and you pull two off and you switch them, then you end up with an R. Are we all right, that friends? Okay, all right. Questions for me? Concerns? Complaints? Don't forget you have a quiz today. Okay. I heard yay and then I heard well, go study then. Okay. So then we took a look at this one right here. And we said draw the enantiomer for the following molecule, and then we drew the mirror image for it, right friends? And I said, okay, the bottom of the question says, is it R or is it S? And it says draw it with dashes and wedges. And I said, let's come back to this because we're getting a little bit tired. And if we do it at the beginning of next class, we're a little refreshed and maybe we can do it a little bit better, okay? So, let me go ahead and erase that right there. And we'll go ahead and we'll draw the dashes and wedges in. Now with the Fischer projection, we said that the horizontal bonds, what does that mean in the Fischer projection? Is it going back or is it coming out at you? It's coming out at you. So those two, you would draw them. If you were to draw in the dashes and wedges, you would do that. Okie dokie smokies? And that means that the vertical ones are doing what? Yeah, they're going back. Now, where did you see that? Well, that so happens to be right there. That up there will show you the same thing. See how the horizontal ones come out at you and then the vertical ones go back, and it shows it to you right here also. You guys see that? You okay with that? Kind of, sort of, maybe? So in case you needed to see it again, let's see, we've got this like this. So our green and our red are going back, and our blue and our yellow are coming out at you. You all right with that, friends? So this is the same thing. I just got to turn my molecule around like that. And see, I didn't break any bonds. I didn't make any bonds. I just twisted my molecule around, which happens in your beaker and your test tube. As long as you're not breaking any bonds or making any bonds, you get the same thing. And we have the horizontal ones coming out at you and the vertical ones going back. And if we wanted to do something like this, which we're used to, we would just go ahead and tilt it down like that so that the hydrogen is pointing up. And we would twist around so that the blue is this way, the red's coming out at you, and the green's going back into the board. Okie dokie, smokies? Can you see it now? How it's all exactly the same thing, it's just different ways of drawing it. So if you're a sugar chemist, you're gonna draw a whole lot of Fischer projections. That's just what sugar chemists do. And they all have their own little quirks and things that they like to do, and then we try to ram it all into a book and like force feed it to you guys, right? Open your mouth, here is a fire hose of knowledge, right? Okay, so are we seeing it a little bit better now, friends? No answer? Okay, all right. And then this one is a whole lot more complex. And then we said, okay, now that we drew in the dashes and wedges, do you guys need me to do it for the enantiomers? Are you okay with the fact that the horizontal's poking out at you and the verticals are going back? One yes. Good. Okay, whoever said yes, thank you. Now the question is, which is R and which is S? I would not ask a question like that to you on an exam. For this class, I would give you either R or S and ask you what the other one is. So if I give you one enantiomer and it's R, the other one's going to be what?
S.
Yay! Okay, and vice versa. Okay.
Give us lots of those.
Give you lots of those. And then we talked about slides ago how I said, how do we know what R and S are? And I said, well, those are the Kahn-Ingold-Prelog rules, and if you were to take organic chemistry, the whole year-long series, you would learn how to identify an R and an S. And I said, don't worry about those slides. You guys remember that? And we said, what Kahn-Ingold and Prelog said is, wherever you have the heaviest atom, that's going to be your highest priority, so that's going to be a number 1. So if you look up there, what we have here is we have a hydrogen, a carbon, and a nitrogen bonded to that central carbon there, that chiral carbon. Now, who is the lightest of the 3? Hydrogen, carbon, or nitrogen? Hydrogen. So we all remember from the periodic table, at least the hydrogen was up at the left-hand corner and it was the lightest, right? Okay, so Kahn-Ingold and Prelog said that the heaviest is the priority. So hydrogen is going to be the lowest priority. It's going to be number 4, even though that's like the highest number. 1, 2, 3, 4. Sorry, chemistry's like that. Are you guys getting used to that now? Like, oh, that would make sense. Oh, it's completely opposite because this is chemistry. So anyways, all right. So let's just call that number 4 because that's our last priority. Now looking at nitrogen and carbon, does anyone remember which one is heavier? Nitrogen weighs 14 and carbon, does anyone remember what carbon weighs? 12, yeah, or the average atomic mass is 12.01. You remember that kind of sort of maybe? And if you didn't, that's okay. You would just whip out a periodic table and you'd be like, oh, there it is on the periodic table, okay? I know these are in my head because I've been teaching it since Jesus took my class, okay? So, all right, so nitrogen is going to get priority number 1. And then we have carbon versus carbon, and we're like, that's a problem, right? But Kahn-Ingold and Prelog said, oh, we have a rule for that. So what you do is you go out to the next atom. So CH3 there on the bottom, you're at carbon, and all 3 of your next atoms are hydrogen. And then on the top, what CO2H means is this. If you drew it out, the structure, it would be like that. Okay? So that top carbon is double bonded to an oxygen and single bonded to an oxygen. So which do you think gets priority? The CO2H or the CH3? Yes. And that's because an oxygen is heavier than a hydrogen. Okay? So this one on the bottom right here, it's only bonded to hydrogens, and that one up there, it is bonded to a couple of oxygens. So the one on the top gets number 2, and the one on the bottom gets 3. So, whew. Also, you guys, I would not make you do this. Just so you know, so you're not out there freaking out. I'm just showing you how this is done, but I will not make you prioritize like this. Do we all got that? Okay. All right. So, all right. So, let's line these up. So we've got blue here, and we've got hydrogen there, and let's make the methyl down there, and then do that up there. Let me label them. Okay, so I'm gonna make this one the green ball, and the nitrogen gets the blue ball, and I don't have yellow, so we'll just have to imagine that our hydrogen is over there. Okay. All right, are we okay with that, friends? Okay, so if you remember from the con-angle Prelog rule slide, it gave you that little wheel thing. Where are you? Oh, here we are. Okay. And what it said is, it said, wait till you sneeze. Okay, I don't think the second one's coming. No, I'm getting it tickled. Okay. All right. So priority number 4, it goes back, so you guys see the dashed line there. We okay with that? Okay. So what we did is we said that this was number 1. We had our green as number 2 and our red as number 3. So it's not coordinating back there, but we are going 1, 2, 3, and we are turning it to the left. So this would be S. Are you guys okay with that? They did their colors differently, but we did 1, 2, 3. If you look at what we circled, so we're going this way. So this would be an S. Are you guys alright with that? Kind of, sort of, maybe. You just trust me, right? Yes. Okay. So here's where you guys need to tune me in. This right here is S. You would need to be able to draw the enantiomer for that and tell me that that one is which enantiomer. Yay! A pluses for everybody! Are you guys alright with that? Okay. So, this is the mirror image of this, and if this one is S, then that one must be R. And then we talked about D and L, and we talked about dextrorotatory and level rotatory, and how dextrorotatory and lever rotatory doesn't always correspond with R and S, that sometimes if you rotate the plane polarized light to the right, that sometimes your chiral carbon is R and sometimes it's S, and if you rotate plane polarized light to the left, sometimes your chiral carbon is R and sometimes it's S. Do you guys remember that? How we wanted dextrorotatory to always be with R and level rotatory to always be with S, but this is chemistry, so ha 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 ha, right? But the thing that did make sense is that if one enantiomer is S, the other will be R, and if one enantiomer is D, the other one will be what? Good, okay? So if I gave you D-glucose and I said draw the Fischer projection for the enantiomer of D-glucose, I would expect you guys people to do this and then name it as L-glucose. Does that make sense, what you're expected? Okay. And then how many chiral carbons do we have in glucose? 4. This one is not chiral and this one is not chiral. And then somebody in here asked me, do I have to draw the carbon here? Because on another slide we had D-glucose and they just put it at a little elbow. And that was fine to draw it that way. So I think I answered that question after most people had packed up to leave. So you guys see it here how these achiral or non-chiral carbons are drawn in as a C. And then up here, it's not drawn in with a C here, but it does not have perpendicular lines. It's at like an elbow. Do you guys see that? The difference? Yes, no, maybe so? Okay. Also, this carbon is double bonded to an oxygen, and then we know so like it can't be chiral, if we want to explain it that way. Okie dokie smokies? Yes, no, maybe so? Okay, you guys look like you're ready for spring break. Are all your kids on spring break like mine are? No. I leave in the morning and they're sleeping and I'm like, must be nice. Oh, I have, my son is in boot camp in, the week after spring break. I will not be here on Wednesday because I got to fly out to Chicago to see him graduate. But I'm trying to get somebody to sub for the labs. But I'm assuming everybody will be okay if I just do like an online lecture like I've done for a few of the, you guys are all right with those? Okay, so, and I'll let you guys know in advance the exact date, but it's the Wednesday after spring break. Yeah, so lab might be canceled that day, lab might be out. I just gotta see if I can get a sub for you guys. But don't worry, everyone in the chemistry department is wonderful. Okay, so, oh wait, was that a question? No, that was just chat? Okay. So on number 2 there, we answered that question, folks. We had 4 chiral carbons and we drew L-glucose. Any questions for me? Okay, do you notice in the D-glucose how one of your OHs is green? Do you guys see that? Okay, so if your bottommost chiral carbon has its OH pointing to the right, like that, okay, your sugar's gonna be a D. Yes?
I have a question. Why did the O switch in this slide, but in the slide where you introduced the D and L, it didn't switch?
Why did he? Oh, okay. Yes. Okay, so do you notice how on all the chiral carbons we drew it exactly mirror image? And students, like if I tell you these are mirror images of each other, like when I was a student, this drove me crazy. I'm like, I want you to draw it a mirror image. I want this one to be switched around too. And then most of the time, chemists just don't do that. They draw the chiral carbons opposite and stuff that's not chiral. They just draw it left to right because in English we write things left to right. So that's why I drew this one that way. I was like, if you like it like mirror image like that, go ahead and draw it that way, but you'll also see it where it's drawn the other way because that's not a chiral carbon. So you can also draw that one like that because a lot of times like chemists just leave the achiral carbons just as is because chemists are lazy like that. Yes, question in the back.
So on the example, it matter?
It will matter at the chiral carbon.
Right, but then to the top part.
The top and the bottom, no, because those are achiral. So the question was, why did I do it mirror image on the top and not on the bottom, and then backing up to the first D and L glucose, it was the same orientation. I believe that was your question, Howard?
Mm-hmm.
Okay, so yeah, that's the reason. So you can draw this one like that and that one like that if you're definitely like, I need this to be complete mirror image to visualize it, okay? And then there's a few people in lab who, like if we had a VR, where like something like that. You don't need to do that, you guys, okay? Just imagine like that's a green ball or a red ball on something like this, okay? Like you don't need to do that. Does that make sense? Like you don't have to draw the BR upside down or anything, okay? I'm not making fun of you, Heidi. I'm like literally saying you don't have to do that. You want it to be very precise, right? Okay. Okay, so I just want to go over the isomer flowchart one more time for us. So the one that we had at the beginning of the chapter looked a little bit different, but it's saying the same thing. So what we are doing in lab is we're saying, here's a couple of molecules. Are they unrelated, so they have different molecular formulas? Are they exactly the same, or are they isomers? And if they're isomers, they will have the same molecular formula. So like how many carbons do you have, how many hydrogens, how many oxygens, but no clue to the connection of the atoms, okay? And if they do have the same molecular formula, they're isomers, and then we split them up into different kinds. So the constitutional isomers, you have the same molecular formula, but you have a different connection of the atoms. So if you go to name both of them, you might notice that the number is different at the beginning. And in lab, I believe we had 2 iodohexane versus 3 iodohexane for those 3 labs that have already gone. Okay, so that's where we have the constitutional isomers. Now, if you have the same molecular formula, but you have the same connection of atoms, but somehow it's different, then we have stereoisomers, and we can split the stereoisomers up into enantiomers and diastereomers. And diastereomers are also called diastereoisomers. So if you see it spelled like that, yep, same thing, okay? And I believe Connie said that those are just the disasters or whatever. Is that right, Connie?
Yeah.
Okay, all right. Those are the D ones. So the isomers that are enantiomers, they've got the same molecular formula. They have the same atom connectivity, but they are non-superimposable mirror images. Okay, so you can't turn one and put it on top of the other and make it exactly the same. So if we take a look at these 2 molecules right here, hold on, let me put them down on the table. Works a little bit better for my brain like that. Okay, so do we have the same molecular formula here, friends? Yes, you have the same number of carbons, so it would be C4, and the same number of hydrogens, 9, C4H9, and then whatever the green thing is, chlorine or bromine or whatever, okay? Same molecular formula, is the same connection of atoms. Yeah, we got a CH3 on the end, bonded to a CH2, bonded to a carbon that's bonded to a hydrogen and a green blob, bonded to the CH3s on the end. So same connection of atoms, right? But when you go to superimpose them, stick this one on top of this one like that, can you see how they don't line up? But they are mirror images of each other. So if you put a mirror up like this, that's what you would see. Or you can turn them this way and say, if you put a mirror up for this one, this is what you would see. Does that make sense, friends? So they're non-superimposable mirror images. Same molecular formula, same connection of atoms, non-superimposable mirror images, okay? Now this is one enantiomer, this is the other enantiomer. What we learned is that if you switch 2 of the groups on the chiral carbon, you will then create the other enantiomer. So, if I take this one, and it doesn't matter if this is RS, if I pull two of the things off and leave the other two, break those bonds and remake those bonds, all of a sudden, I've made the other enantiomer. You guys see how that's exactly the same now? Okay, so that was that part about switching the thingamabobbers. Two of the groups on the chiral carbon. Okay, so what happens if you're not non-superimposable mirror images, but you have the same molecular formula and same atom connectivity? Well, that would push us over to the diastereomers. And the group of diastereomers that we've already learned about are the cis-trans isomers. You guys all right with that? And I said there's some other ones, we just haven't learned them yet. Well, here we are, we're learning them. So this is going to be the configurational diastereomers. And this happens when we have more than one chiral center. So if we look at 2,3-pentane diol, let's go ahead and identify where our chiral centers are on 2,3-pentane diol. So first of all, friends, we've got pentane, and that's going to tell you that we've got how many carbons in our parent chain? 5. Are we all good with that? Chapter 12. And then it says diol. So it's telling you you've got 2 OHs somewhere on that 5-carbon chain, right, friends? Where are they? They're at carbons 2 and 3. Okie dokie smokies? Okay, so the first carbon up there, it's labeled number 1. Is that chiral? No, because it has more than one hydrogen, so you have the same group there. And remember, to be chiral, you have to be bonded to 4 different groups, so not chiral there. Number 2, you have a carbon that's bonded to a methyl group, right here. It's also bonded to a hydrogen, it's bonded to an OH, and it's also bonded to this big blob over here. Don't even worry what is over there. It's different, whatever it is, it's different from OH, H, and CH3, right, friends? Okay, so is carbon number 2 chiral?
Yes.
It sure is. Okay, so I'm gonna erase that. And we're gonna put that one's chiral. Okay, how about number 3? Yes, and if you have to circle things, okay? It'll help you, like make a visual. Take the hydrogen and circle it. And you can see that the hydrogen and the OH are different. Are we okay with that? And then say, okay, it's also bonded to CH2, CH3 to my right. And it's also bonded to something to the left that I'm not even gonna try to name or anything like that, but that thing over there is definitely different from the OH, the H, and the CH2, CH3, right, friends? Okay, so is carbon number 3 chiral? Yes, it's bonded to 4 different groups. Now, when we have a cyclic structure, so say carbon 2 and 4 were somehow connected like that, sometimes it just like frazzles our brain. But what you can think is, if you're heading on a drive that way, do you see different things than if you're going that way? And the answer would be yes on this one, okay? So don't let the cyclic structures bug you. So yes, number 3 is chiral. All right, what about number 4? Nope, it's bonded to 2 hydrogens, and those things are 2 the same thing. What about 5? Nope, bonded to 3 hydrogens. Those are the same. Okay, so we've got 2 chiral centers. So our chiral centers can be R or S. It just depends on the molecule. And 2,3-pentane diol, you can get all of these. So you can get where carbon number 2 and it's backwards, because my brain wants to go 2, 3 like that. Doesn't your brain want to do that too? But no, they had to put it like this way, and I'm like, why? But anyways, 2 and 3 are S, that's the orientation. So if we were to draw the enantiomer of this one, it would be the exact opposite. So if 2 is S and 3 is S, then in the enantiomer you have to have 2R, 3R. So these two right here are enantiomers because all of the chiral carbons are exactly the opposite. So now I'm going to the bottom two. We have 2S, 3R, and over here we have 2R, 3S. Is this one the opposite of this one? Yes. 2 is S here and 2 is R here. 3 is R here and 3 is S here. So these two are what? Those two are enantiomers of each other. Okay, now let's grab this one and this one. Do they have the same molecular formula? Yes, they do. So they're some kind of isomer, right? Do they have a different connection of atoms? Nope. They're both 2,3-pentane diols, right? Right? Okay, so they're not constitutional isomers, so that brings us over to stereoisomers, right, friends? And then we split into enantiomer and diastereomer, right? Are you all with me? Is this one a mirror image of this one? No. And to be enantiomers, you have to be mirror images. You have 2S and 2R. So, okay, that one qualifies, but then you have 3S and 3S. They have to be opposites at every chiral carbon. Are we okay with this? So if you're not an enantiomer, that throws you into which category? Into the diastereomer category. Are we all right with this? Okay. And they're not cis-trans isomers. So we would call those configurational diastereomers, but we can just call them diastereomers. All right, friends? Are you okay with that? Okay. So this way, these ones, are you all right if I just put the D there? Okay. So what about this 2,3-pentane diol and this 2,3-pentane diol up here? These are what? Disasters? Are these also diastereomers, folks? Yes, you have 2S here and 2R here, so okay, maybe they're enantiomers, and then you have 3R and 3R. Okay, so they're not complete mirror images, so that throws us into the diastereomer category. Are we okay with that? Okay. Questions for me? Concerns? Complaints? Okay. All right. So just in case you didn't like our 2,3-pentane diol example, here it is again in general form. And you can see that if you have exactly the opposite at your chiral carbons, you're enantiomers. If you don't, then you're diastereomers. So I guess I went crosswise, but I forgot to go up and down. So these ones and these ones are also what? The D one, right? Diastereomers. Or diastereoisomers. Disasters, yes. Okay, questions for me, folks? Okay, so Fischer projections make it pretty easy to see if something's an enantiomer or a diastereomer. So right here, at our chiral carbon, so you can see that it's drawn opposite. So those are enantiomers, because that was a mirror image of this one. Are you guys okay with that? And over here you can see that these molecules have how many chiral centers? How many chiral carbons? 2. And in order to be enantiomers, everything has to be a mirror image. So this one is a mirror image of this one, but this one is not. It's the same. So it doesn't qualify as an enantiomer, so then it just falls into the diastereomer category. Okie dokie, spunkies? All right with that? right, last slide. So we've got some sugars here. So these are called aldoses because at the top they have an aldehyde functional group, and that's the next chapter, aldehydes and ketones. Aren't you guys excited? So which are enantiomers and which are diastereomers? So we're going to look at all of our chiral carbons and see if we have exactly the opposite in each one. And if we do, they're what? Enantiomers. And if we don't, then they're what? Diastereomers. So can you see how the Fischer projections make it a little bit easier? Yay! Okay. And again, you guys, ignore this one and these ones at the top because they're not chirals. So we're not looking at those, all right? So the first two, are they mirror images? Yes. And again, remember, you're looking at the chiral carbons only. If you need to draw this way and this one that way, okay, do that for your own mind. I used to have to do that when I was a student. I mean, like, scroll it on, you draw a mirror image, draw a mirror image, right? Okay, so these two are enantiomers. All right, what about 2 and 3? Are they completely opposite at every chiral carbon? No. This one right here, those are opposite. This one's the same, right? Do they have the same molecular formula? So 1, 2, 3, 4, 5, 6 carbons, same number of hydrogens and oxygens. Okay, the same atom connectivity. Yep, so those ones are what? Good, diastereomers. What about 1 and 3? Enantiomers or diastereomers? Good. This is not on the quiz. Those of you who have lab this afternoon, you might want to wait until we do lab before you take the quiz, because there's a couple of questions where I talk about enantiomers versus the same molecule versus diastereomers, and it's very similar to something that's on the quiz, and it might help you, okay? All right, questions for me, folks, before we end a little early. Okay, so if you want to stay and ask questions like it's an office hour, please feel free. I am paid until 2:10 to be here in the lecture room. If you feel like going to lunch, okay with me. Again, don't forget your quiz, folks. Okay? Questions?